So we have seen the sequences and their limits, then limit theorems, the monotone sequences, and the convergence and divergence of the sequences of real numbers. Right? So let us see one more theorem. And the statement is that if sequence Sn is a convergent sequence, and if A is less equal Sn is less equal B, that means every term of the sequence is bounded for a positive integer n, then the limit of the sequence Sn is also bounded by A and B. The statement is enough. The next theorem is squeeze theorem. And the statement is that suppose sequence Sn, sequence Tn, and sequence Un are sequences of real numbers. Such that Sn is less equal Tn is less equal Un for all positive integer n or natural number n. That means nth term of the sequences are like that. Every nth term is this. And limit of Sn is equal to some L and is also same as limit of sequence Un. Then sequence Tn is convergent. And their limit is also same. Limit of Sn is same as limit of Tn is same as limit of Un, and it is L. It means what? If sequence Tn lies between sequence Sn and Un, and both these sequences are convergent to the same limit L, then the middle sequence will also converge and the limit will also same as L. So let us prove. Proof is also very easy. Let L is limit of sequence Sn, which is also same as limit of sequence Un. It means what? By the definition of limit of a sequence for any given epsilon greater than 0, there is positive integer n such that the difference Sn minus L is less than epsilon for all n greater equal the positive integer n, and difference Un minus L is also less than epsilon for all n greater equal L. So as Sn is less equal Tn is less equal Un for all positive integer n, so it implies that for any real number L, Sn minus L is less equal Tn minus L is less equal Un minus L, because it is the property of real numbers. If A is less than B, then for any real number C, A minus C is less equal B minus C, A plus C is less equal B plus C, right? And it should be true for all positive integers n. But it implies that Sn minus L is less, as Sn minus L is less than epsilon. So by using property of absolute value, right, it means that minus epsilon less than Sn minus L is less than epsilon for all positive integer n greater or equal n, and minus epsilon less than Un minus L is less than epsilon, right, by using the property of modulus function or absolute value function, right? So this thing is strictly greater than minus epsilon, is less equal Tn minus L is less equal Un minus L, and Un minus L is strictly less than epsilon. It means what? That is minus epsilon less than Tn minus L is less than epsilon, and with n greater equal n, n greater equal n, that is Tn minus L is less than epsilon for all n greater equal L. It means that limit of sequence Tn is also same as n, and it is what we wish to show. For example, limit of sequence sin n upon n is 0. Why? Since it is bounded by, it can be written as minus 1 by n less equal sin n by n is less equal 1 by n, right? And sequence minus 1 by n converges to 0, sequence 1 by n converges to 0. So by squeeze theorem, sequence sin n upon n will also converges to 0 by using this theorem. Then what we left in this chapter? Then the next thing is calculation of a square root. So let A is positive integer, positive real number, and we construct a sequence Sn of real numbers. Sn of real numbers that converges to square root of real number A. So let S1 greater than 0 be arbitrary number. Arbitrary real number. And now we define Sn plus 1 to be half times Sn plus a upon Sn when n is positive integer or natural number. So we show that sequence Sn converges to square root of a. So to show this, we first show that the square of Sn is greater equal a for all n greater equal to, as Sn satisfies, as we have defined Sn plus 1 to be this. So from this expression we can say that, calculate this thing, make this cross multiplication, so it will be Sn square plus a divided by Sn. So transfer this 2 times Sn on to the left side, so we can have Sn square minus 2 times Sn plus 1 into Sn plus a to be 0. And this equation, which has a real root, it has a real root, therefore this thing will be greater equal a for all n greater equal 1. And now consider Sn minus Sn plus 1. So Sn minus Sn plus 1, we have defined it to be half times Sn plus a upon Sn. So it is Sn minus half Sn, so it is half times Sn. Otherwise make the cross multiplication, Sn square plus a, and this is Sn square minus, Sn 2 Sn square minus Sn square. So it is my Sn square. So it is Sn square minus a divided by Sn. And this thing will be greater than 0 or less than 0. Sn square minus a. This thing is positive, as Sn square is greater equal a. Yes. So whether it is greater than 0 or less than 0. Yes, S1 is greater than 0 is arbitrary, and we define definitely Sn is greater than a. So Sn square definitely greater than a. So this quantity will be greater equal 0. So this is greater than equal 0. But it means what? That is Sn minus Sn plus 1 is greater equal 0 means implies Sn plus 1 is less equal Sn. That means the sequence is a decreasing sequence, right? The largest term is less than the term before that. So is sequence Sn is a decreasing sequence. Therefore, monotone convergence theorem implies that sequence Sn is convergent, because it is a non-increasing sequence which is bounded below, so it converges, right? converges to some limit, so say S or L we can use in. So S is same as half times S plus A upon S. Yes. So it implies that now simplify this thing. So simplify this thing. It is S square minus two S square minus S square, so S square minus so how can simplify this thing? So it implies that if we solve by this way, S equal to half times S square plus A divided by S. So if we solve like this, if we shift this to S to the left, so it is 2S square is equal to S square plus A. So it implies S square equal to A, or if we shift this 2 on left, so it will be 2S equal to S plus A by S. That means this will imply S equal to A by S. So we will either get S equal to A by S or S square equal to A, and both are the same things. So that is, this implies that S square equal to A implies that S equal to square root of A. Right. The next thing is Euler's number. So the sequence En, which is defined to be 1 plus 1 by n raised to n for positive integer n. So it is sequence, this sequence En is bounded and increasing, bounded below and increasing, and hence every sequence which is non-decreasing sequence bounded below is a convergent and is convergent. Thus this sequence En converges to E, which has the approximate value 2.7182, something like that. And the last thing of this chapter is that the Bolzano-Weierstrass theorem. And we are going to see the statement only. A bounded sequence of real numbers has a convergent subsequence. A bounded sequence of a real numbers has a convergent subsequence. Okay, so you have to complete some assignment. Next one is assignment 5. You have to complete and submit all the assignments within 3 to 4 days. If a is greater than 0, then limit of the sequence 1 upon 1 plus NA is 0. Show that it is convergent and converges to 0. Number 2, if C is greater than 0, then limit of the sequence C raised to 1 by n, it is convergent and converges to 1, and also limit of the sequence n raised to 1 by n is also 1. Number 3, write first 5 terms for the sequences Sn is 1 plus minus 1 raised to n, and sequence Tn is 1 upon n into n plus 1. The next one is show limit of the sequence 2n upon n plus 1 is 2. Show limit of the sequence 1 by n minus 1 by n plus 1 is 0. Next one, show limit of the sequence 1 by 3 raised to n converges to 0. All are similar examples. Limit of sequence n square by n factorial is also converges to 0. And the next assignment, number 6. Number 1, show that limit of the sequence 2n plus 1 divided by n is 2. Number 2, show limit of sequence sin n divided by n is 0. Number 3, show that the sequence 2 raised to n is not convergent. Number 4, show that the limit of sequence 1 by square root of n is convergent and is converges to 0. So complete these assignments and we'll start next chapter in our next lecture.